And start the recording. The speaker for this general lunch is Dicman Alfred, and he will be presenting a new methodology in determining well spacing in unconventional reservoir, a Delaware Basin study. Dicman Alfred is currently a Director of Subsurface for SOTAOG or SOTAOG, heading the real-time production optimization and predictive analytics group. He has 18 years of unique experience in the geoscience and engineering domains. His areas of focus include business development, petrophysical modeling, interdiscipline integration, geocellular modeling, analytical reservoir performance analysis, production optimization, completion design, data analytics, and machine learning. So quite a lot of things that Dikman has a lot of experience with. He has agreed for this talk to be recorded. So thank you again for that, Dikman. And you can see that talk will be posted to the HGS YouTube channel. Please go to the event page to see where you can find that link. And with that, I'm going to go ahead and give the floor to Dikman.
All right, so before I begin this talk, I'm just going to make sure that that's not the same shirt. Okay, I don't know how that happened. But anyways, I'm going to begin my talk by introducing the topic. So it's called the new methodology to get well spacing for your unconventional reservoirs. Even though the topic is about well spacing, there's a lot that comes with it. So as you go through this presentation, I will explain it to you one by one. So I used to work for my previous job was at Scala Energy, where the last 5 years we worked and we developed the Permian acreage. And during that process, I was able to look into multiple data rooms and data. And most of the idea for this methodology came from looking at the data. We're looking at across the basin. We started seeing some trends, and that's what's the underlying idea behind this methodology. So I'm going to go ahead. Let's go. Okay. So what's the problem statement here? So it only took 2 articles in the Wall Street Journal, and that pretty much destroyed our industry. Okay. One was spacing, and the other was GOR. Okay, so, and frankly, we haven't recovered from that damaging articles. Okay. So, well spacing is always going to be our biggest concern as we move along the unconventional reservoir development. The second thing is, I know big companies or mid-sized independents, they do pilot studies. You know, one is time consuming. You've got to get all the data, core data, microseismic, you know, frac data, different science experiments, and all of that. The problem is, you can't do that everywhere. You know, it's time consuming and expensive, so you can only do it at certain parts. And we know that the shale plays are anything but homogeneous. Okay. The third thing is, can we reduce cost? And moving forward, this whole industry will be about cost cutting, cost optimization. Can you reduce cost as much as possible? Okay, can we do that? And the last thing is, everybody talks about this, but there is nothing like concrete or set in stone. Everybody says, I need to do this completion design by geology or landing target. Well, it's all nice to say this, but end of the day, your completions manager is going to get really pissed off if you tell him I have 15 designs for all the lithologies I encountered. Practically, it's not possible. It's just operationally, it's very cumbersome. But what can we do to minimize the operational hazard? So before I even explain the talk, here is all the results that's going to come out of this methodology. So keep this in mind. So the first result would be you would see the impact of your geology with respect to your completion design. So whatever design you choose, you would see the impact of what geology that you practice. And the faults and fractures. So one of the biggest thing that we noticed was this methodology was able to identify your existing faults or your interpreted faults from seismic, or where the seismic guy didn't know where to draw the line through the wellbore, so you can see that. And also it can also help you identify which are the fractured areas in terms of, you know, like a permeability thing. You know, are these the stages going to go longer? You know, so. And the other one is this is very important. Usually we know that the geology changes along the wellbore. But we don't know how pressure changes. It's impossible to come up with the pressure changes right now. Like there are some companies talking about this and see if we have depleted zone as you travel. But right now, in terms of to do that with a simple data set, is not possible to come up with has the pressure changed along the wellbore. Okay. For me, this is the best part for the reservoir engineers. After you drill a well and frack the well, you'll probably know what to expect for this well. Are you going to meet your forecast? There is a budget forecast and the AFE was set on a certain type curve. You would know immediately whether this well is actually going to meet the budget curve or the type curve set. Okay, this will help you in setting up your facility and your capacity and stuff. And finally, there will be a optimum well spacing. So just to tell you, so this is going to be done on a pad by pad. So you need to have a parent well somewhere. So that's what you need, a parent well to even do this methodology. So you're going to come up with the spacing based on the parent well, what happened to the parent well. And based on that well spacing, you're going to come up with what design should go. If you're planning for a 6 wells or a 4 well pad, what design should go. And the key thing is save on fluids. Fluids are a significant cost, and the whole talk is going to be about fluids. Okay, and we can all do that with no additional data cost. You're not going to go back to your boss and says we need this data. No, it's already data that you already have. Okay, that's the best part about this methodology. Okay, so this is the usual multidisciplinary integration. So I'm not going to go all of this. I only want you to focus on this side. So what does the geologist get? They will get a local reservoir characterization. That means their seismic is big, it's too big to go to a pad level. Okay, you can do it, but this one is telling you how minute and detailed you can get in a pad. Reservoir engineers, they will get an idea of what the type curve should look like, whether they're going to meet the type curve for this for the well they just fracked. Okay, and the completion engineers will already get a design based on lithology and landing. Okay, so let's move on. So what's the methodology? So if you look at the top there, I wouldn't want to name this wise guy, but he said, fluids do the work, proppants take the credit. It's actually true, because think of this. So when you frack a well, you send the fluids first to frack it, and then you send the proppants. All that the proppants doing is sitting inside those stimulated fractures and getting pressed. That's all it's doing. Now the fluids are the guys who are going inside, doing the dirty work, and getting the hydrocarbon, displacing it, changing wettabilities, and coming back with it. And the proppants, all it does is it sits there, getting pressed, gets the fluids into the wellbore, and suddenly the whole industry praises the proppants. I mean, when you look at things, everybody wants to plot EUR as a function of proppant per foot. It's good, but seldom you see EUR as a function of fluids per foot. If you plot that, you will find an equally interesting correlation. Okay, and our industry, everybody talks about this prop XF. It was like I've been working in shale plays for the last 12 years now. Everything was about prop XF. Your RTA work, your simulation work, everything, and you might have heard these numbers: 130 to 150 foot. That's all we have prop XF. I'm sorry, we've done this. We failed. It's time to look to another methodology. Okay, and this time it's all about the fluids. Okay, let's talk about the fluids. So I'm going to explain this graph I know there are a lot of geologists, but I'll try to explain in a very simple way. We frack, this is a typical stimulation job. We pump the fluids, the formation breaks down here. We continue to pump the fluids. Once it breaks down, we have the fluid leaking into the fracture, from the fracture into the matrix. Okay, so you created a fracture, the fluid starts leaking. At some point, you stop pumping. You remove all the friction, everything stops. But even after you stop pumping, at that point, we measure something called a shut-in pressure. Okay, even after we start pumping, the fluid still continues to leak off because you have created some pressure inside those fractures. It's going to leak off. And after a long time, we don't know, maybe 2 weeks or 3 weeks of an actual job, the fracture closes. Okay, now even after fracture closes, you have some fluids sitting inside the pore space created by the proppants. It'll still leak off. It's sitting at a higher pressure. And at some point, all the fluid will go in because there will be an equilibration created from the stimulated fracture and the matrix. At that point, there is no movement of fluids from the fracture into the matrix. And that is the point I'm interested in to say, I need at some point in time, how much of this fluids have gone into this matrix, okay? Is it possible to estimate this in a real-time job? No, you can't. So it is also important to note, even after the fluid leak-off stops from the fractures into the matrix, the pressure is still dissipating into the matrix. The pressure continues to leak off. And this is what people do typically when they want to establish a reservoir permeability and pore pressures. They analyze this part of the curve, your pseudo-radial flow. We don't have time for all that, okay? But I want to know at what point I've completely expelled all the fluids into the matrix, okay? And we're going to do that by two measurements. Standard things that you already see in your daily, in your company, your ISIP, and your change in ISIP with time, whether it could be 5 minutes or 10 minutes or 15 minutes. And I will have a comment on which one to use. I mean, the more the better, obviously, but most people will have 5-minute data, and that's the data we're going to use. And I'm going to explain to you how it's going to look, okay? So let's consider 3 stages, okay? We have 3 stages, 1, 2, and 3. You have the same surface area created by the, your fracture, okay? But your geometry is different. Maybe the width is smaller here, is big here, it's a large here, okay? Now, consider if the permeability is the same, the pore pressure of all those 3 stages are the same, okay? Once you stop pumping, P1 is sitting at a very high pressure than P3. Just because you have a smaller volume and I pump the same fluids into the smaller volume, obviously I have the higher pressure. When you start leaking off, that is your delta ISIP at a specific time, let's say 5 minutes or 10 minutes, you're going to see something like this. Because you have higher pressure, you have the same permeability, so the same surface area, you're just going to leak off faster. There's be a lot of leak off compared to the one that had a lower pressure. It's just pressure dependent leak off, it leaked off. Now, the key to the methodology is instead of looking at each individual point, I'm going to look at a collective view of the stages. Okay, now, if I look at the collective view, I will all call this, it's the same frac job. It's just that it's got different geometry, but the surface area I created is the same, okay? And here's the interesting part. When this gets to 0, what does this state imply? This says at 0 delta ISIP, that means I have no more pressure to lose, right? And that's when I stop the fluid transfer. The fluid doesn't move after 0. Okay, if it's still moving, then there will be some pressure drop. But at 0, you extrapolate and you have this thing called equilibration pressure. That's what when I meant by the previous picture, I need to find that point. And you could find the point like this, okay? And if you know the pore pressure of the system, guess what we did? That's the delta P that you have introduced into the system, okay? And larger values of delta P implies that your volume of your affected volume is very small. If you have a smaller delta P, then you affected a larger volume. Very simple, right? You have smaller volume. If you pump this same volume, you pump the same fluids, you get a higher pressure. So pretty much consider this transfer function like a lambda. If you're familiar with fractured reservoirs, the lambda is like how this thing leaks off. Your transmissibility. Okay. So this transfer function is going to be a function of 3 things: your surface area you create, okay, your reservoir permeability, and your reservoir pressure. Pretty much this area, your reservoir permeability and pressure. So how do you interpret this? So before I show the results, I want you to get an understanding. I want you all to understand how do you actually interpret this transfer function. Okay, let's move on to one simple thing. Let's say you have the same well and you have completed this with 3 different completion strategies. Let's say you have 5 stages each. You did 3 different completion strategies. Now, just by looking at this, your surface area that has the highest slope, the slope will have the highest surface. The one with the highest slope will have the highest surface area, because you will leak off faster if you have a larger surface area and the slope will change. Okay, so just by looking at how the slope is changing, you would know that that surface area, number 3, is you didn't create much compared to number 1. Okay, is it good or bad? That's a different question. But surface area wise, you did not create much surface area compared to number 1. So how does permeability affect you? Again, let's assume you have 3 wells with 3 different permeabilities of the formation. If you have very high permeability, obviously you're going to have a higher leak off. Okay, you have the same reservoir pressure, it's just the permeability difference. And you have a very low permeability, this function is going to shift to the right. Okay, that means you are going to have a lower leak off because you have lower permeability, and you're also creating, remember, this is the equilibration pressure. You're also creating a very high pressure increase into the system. So your affected volume is only a small volume. Okay, that's why you're getting this very high delta P. Okay. And what about pressure? What if you have initial reservoir pressure 1 versus 2? Okay. Automatically, the one with the highest pressure is shifted to the right. So if you think about this, your ISIP here is a function of pore pressure as well, because there is a closure stress involved, and your closure stress is a function of pore pressure. So if not for anything, if you see these two things shifted, you automatically know that one is at a higher pressure than the other. Just very simply, that's the explanation. You could also have the same status if the permeability. So what I'm trying to say is, when you interpret this transfer functions, you have to think of all these three things, okay? Because the way the pressure decreases or increases or decreases is a function of three things again: surface area, permeability, and reservoir pressure. Having got that out of the way, that's the only technical part, or not the only technical part, that's the N-1 technical part I'm going to show you today. And now we are going to talk about the results. Okay, here's the results. First of all, let's talk about faults in regimes and Perm stages. So we drilled two wells, okay? So there was a well A and there's a well B. We knew there was a fault going here, but we didn't know exactly where, but the seismic showed something. And we didn't know what this one was. Maybe there is a fault, maybe not. So we had some idea, but sometimes we thought, okay, this is the direction, maybe this is this way and not this way. So let's look at the results, right? So this is the red part, this is the green part. So when we started plotting these things, it started plotting here, and then suddenly after this fault on the green side, it started going to the lower pressure. Remember, lower pressure always goes to the left, okay? It started going here. Then we started plotting the results of this well B here, and then that one started plotting next to the green stuff. And once we crossed another fault that we thought there is, and then it came to another pressure regime. So there's another region. So right from this plot, you would know that you have three different pressure regions. Okay, you have 1, 2, and 3. Obviously, one is sitting at a higher pressure than the ones in the blue. Okay, that's number one. So you just got your faults identified and everything. Most people have a problem. Okay. When somebody finds a fault, when a geologist identifies the fault, the first question the engineer asks is there a halo of an affected fault zone that I should be not fracking or reduce the size of the job? That question is not easily answerable because some people say, stay 500 feet away from the zone. That's all numbers out of the air. Okay. This one will tell you, okay, whether you had a halo, right? So consider this red versus green. You slowly transition into this, okay? The red one, after you finish, you slowly transition. You didn't have like a jump, okay? So you would know that whether this one has a halo, so you think about what you do on the halo zones. Whereas you talk about the purple versus the blue, it's most likely abrupt. Like if something just abruptly changed from here, it just jumped to this part. Okay. What's the other thing that comes out of this is this high leak out zones. Okay. For example, this one here, these things here. If something is not in zone, so you're looking at a collective view of the stages, right? So something that's outside the variance of this thing, for me, I would interpret this as a very high permeability zone. Okay, it could have a small fracture, or it could have something natural. You could have a lot of natural fractures that could have caused the high leak off. So this is another way to determine which stages would have this high leak off. We'll come back to interpret this as a function of geology, but first thing out of this is whatever you want to interpret geology, that stage A has a higher permeability than anything else. Okay, that's true. Okay. So what do you do with this? So once you identify this, you have to go back and find where that stage is, look at your regional stress direction. And when you start planning wells to the side of well B or well A, you start avoiding putting stages there. Okay, you do not put a stage where there's a high leak off because you're wasting it, and then you're going to hit the other well. You're going to get a frac hit. So those are the implications of this methodology. Yeah, so finally we now say, okay, you could see this fault, okay? Faulted wells, I mean, maybe gas wells, it might help. In my experience, if you find a fault, the well is dead, or pretty much it's not going to work, okay? So it is important to identify the faults. No faults are ever good at least in my experience. So at least you can plan for it, right? You do not want to frack, and if you put another well, you do not want to frack in the fault zone, okay? Because you're going to get frackets. So this is an example of why we can find these things. You know, you can find for high permeability stages, you can find faults. You can also find out if the pressure is different across the fault. You know, three things all in one plot. Okay, let's move on. So effective lithology. Okay, so everybody knows, like, I mean, unless you have the super geosteerer from Mars or something, you're going to traverse. Okay, you're not going to drill the well in the same lithology within 5 or 10 feet. So this is an example of a Wolfram XY well. So we drilled starting from here. So we drilled in one slightly shaly, you know, that X shale or something, and then you drill through the sand, and then you browse through some other lithology that's slightly high. So off the bat, you know that I did not drill this in the same, you know, all my lithology is not the same. So in order to identify what's the effective lithology, you got to do some science. Okay. When I say you got to do some sciences, first of all, you know, you got to find out when you call this facies changes. So this is an easiest example I did. So I used the MSc log, which, by the way, like I hope most people are using MSc logs because it's an amazing tool to do some analysis. So this is just a gamma ray and MSc. So off the bat, from the gamma ray, you could make this out, right? I mean, you could say this high gamma ray is one lithology, all of that is very high. Then you got the sand, and this is just some elevated gamma. So I know there's three parts here. The reason I wanted to put the MSc is I've been using MSc as a great tool in finding out fractures and faults, like fractures most likely. If you have an MSc that does the mirror image, like with the geology and with the high MSc, that's okay because the strength of the rock is reflected in the MSc. But this is not okay. Okay, you have a gamma ray that's flat, but the MSc going high is not okay. Okay, so you expect some things to happen. Most likely, it's going to be fractures. Okay. So we find out those are different phases, you know, those are the high MSc stages. And so we started plotting this thing, and then you see this effect of lithology. Okay. So this is why, and one of the sponsors I talked to was like, I wanted to diversify this because they do the measurements, you know, on this, and it is important to know what's going on in your horizontal. Get those measurements and try to see if you can relate what's happening in this plot with respect to geology. Okay. And that's the part where I'm showing you right now. Right now, I will tell you, if you can keep the stress shedding out of the equation for a while, right now you'll tell me that the lithology one had the highest permeability because it leaked off very high. It created the smallest delta P. So remember, smallest delta P, very high SR, okay? And that's gone big. And while the green here has the lowest permeability. So you have a very high delta P created by the green, assuming that you know the pore pressure. Hopefully you'll know the pore pressure from a DFIT or something. So, and then you have this. So now I know how to connect my lithology to what I treated this, okay? Would I treat this red zone, if I had the same spacing set, would I have treated the red zone or the red facies differently? Obviously, yes, okay? I would have tried to limit my, my fluid design so I do not go beyond what I intended to, okay? This is how you use this picture. So now we have a way, it's just now you have to just convince the completions manager that, hey, this is what I see, you know. So yeah, now we can find the effect. So the another thing I noticed about the Permian is the scatter. So Permian has 4 reservoirs, like a Wolfcamp A, then you got a B, C, and the D. And so what I noticed was the Wolfcamp A has the lowest clay, obviously, and we have a few interbedded carbonates. And if people who know me, I'm very big on this interbedded carbonates thing. So any petrophysical analysis in unconventionals should go, you know, people should create this interbedded stuff because it affects a lot of things, including, you know, your completion design and your ability to access reservoirs. Okay. And you find that the Wolfcamp C here, okay, this is Wolfcamp C, you have a little more clay and you have a little more interbedding compared to A. And D had the equivalent clay, to be honest, but it has the largest or the degree of interbedding, higher frequency of interbedding. And I've noticed this, okay? You get a lot of scatter, obviously, when you get a lot of interbedding, because now you're creating an SRV that's very inconsistent. You're not creating the same thing. You're going one up, one high, one low, because of all this, where your wellbore is with respect to interbedding, the higher interbedding, and your landing target zone. So my takeaway, or what I think it should happen is, if you find your wells have a lot of scatter, go back and rethink your landing zone. Okay, this is like you're reverse engineering the problem. If you have something like this, your landing zone is probably good. You do not have this. You're not creating all this big scatter. But if you have something like this, it's a question of going back and saying, is that your landing? Can you do better with the landing zone to create some nice geometry? Okay. So reservoir engineering, okay. So this is one of the amazing results that we thought we should tell the world is, here's the issue. I'm going to tell you what the wells are, and here's the example, okay. Well A is my parent well. This is the well we drilled, and we know it works. It made X number of barrels per foot. And then we came back and drilled B, C, D, E, and F, okay. These are all the average TVDs of these wells. So B, C, and F are deeper in the basin, and it's all same Wolfcamp A wells, and the D and the E well is shallower than the Wolfcamp A, this parent well, okay. And so that's all given to you, and you have this actual results from completions, okay. So one thing about the Permian is your reservoir pressure is always going to be proportional to the TVD. When I say that, both in absolute as well as gradient, your gradient as well as absolute increases as you go deeper in the basin, okay. One. So let's look at this plot, okay. From basic reservoir engineering, okay, you know that the well is shallower than, if you drill shallower, your energy of the system is lower. So you're expected to have a lower performance compared to A. So you cannot put a type curve of A as good as D or E. D and E is going to underperform for sure, okay, because of the energy of the system. You just can't overcome the energy. So even though you have the same thickness or anything, it's just not possible to overcome the energy of the system. Okay, so you're going to provide, your expectation is D and E is going to underperform A, and D is going to be better than E as well. So here's the red dots, which is the well A. The green is the D, okay, and the brown is the E. So everything went according to expectation. Remember the pressure plot I showed you. Lower pressures gets to the left, the higher pressures goes to the right, okay. Okay, all of this assuming you know the pore pressure here, okay, and I'll come back to that. Now let's look at the well B, okay. Drilled slightly deeper than well B, okay, over here, okay. Where does it fall? It falls here, okay. And so you can convince, or you can tell the management right off the bat, okay, it's going to be the same. You're going to get the same EUR per foot. I don't think, well, if you know the reservoir pressure as well, the same, you can go and tell them, yes, it's going to perform, and it did. So well B was the same EUR per foot as well A. Everybody was happy. Now well C, slightly deeper. I expectation was at least as good as A for sure, or better than A. What happened was it tracked A, but then after some time it went to where the D was, low pressure. The well was not as good, and we had a mid result. Okay, it's not as bad. It's not as low as D, but it's not as high as A. And your pressure shows you that. Okay. The worst underperformer is well F, supposed to be the best well, deeper, all thickness. I mean, given all the geologies, all Wolfcamp was nice things. But what happened was it fell right on D. It had no business being next to this green dots, but it did. So, and of course, you can guess the performance. It was bad. Okay, low pressure. Now, this gives you a chance as a geologist or a characterization person to go back and see. Now, in your characterization, you already have what pressure this should be in. You go find reasons why it should be. Maybe there's a fault cutting this, completely different region. Okay, and this is the example of how you can identify your well ranking immediately after the job is over. Okay, and the one question people keep asking me is, so suppose I drill a well here deeper, and the plot is somewhere here. Is it going to be better in terms of, if I make 100 barrels, I'm going to get 120? No, that's not true. Okay, you can drill a well here in deep part of the basin. Frac job can only access so much. Okay, it's not like the deeper part of the basin you suddenly access the bigger reservoir. It all depends on your frac job. But one thing I can tell you is, if you see this plot, let's assume you have a E well, D well, and A well. You have the luxury of opening up your choke. When you actually do the flowback, you have the luxury of doing a different choke strategy on well A compared to well E. Most people do not like to change the choke strategy, but use this plot and go back and say, I got enough pressure to play with. Why can't I get this reservoir faster, the oil faster out of this? Okay, that's the advantage of knowing where your wells are plotting. Okay, so here's probably like a quiz for you. So we start drilling another well, and we drilled it. Well, G here, same A is there. It's a shallower well. Okay, and here's the problem. It started plotting as good as well A. So everybody was excited as a reservoir engineer, yes. And so first thing for geologists, they know. So two reservoirs are different. You cannot assume now, okay, I got a map here, a thickness map, an isopac. You cannot join these two reservoirs. There is have to be some break somewhere. Okay, that's true because this doesn't happen. Okay. Now we expected to be good, but then your poor pressure results came from a defect. Okay, this is well A's poor pressure. This is well G's poor pressure. So now we know the story. What happened? Permeability. Okay, only permeability can shift it right. You remember, low permeabilities will shift this to the right. Okay. Now, a lot of times you go and look for, how do you look for low permeability? This is something that as a petrophysicist or geologist will struggle. How do you come up with permeability? That is not one tool right now out there. Okay, you just can't get permeability unless you get some, like, you're making some assumptions into permeability. Now, obviously, this will tell you that well G has a low perm, and the well failed. I mean, the well was not a great well. Okay, even though everybody was excited, it's plotting on the same trend. Okay, now the question remains. So we went back to the porosity, and here's one thing that always comes is, okay, the porosity of well A is 8%. The porosity of G is like 7.6. Okay. I didn't expect that to hurt me so much, but people don't know what the difference, I mean, even between 7.5 and 8%, how bad is the permeability change? And that's why getting measurements, as I said, in your horizontal through cuttings to know what's happening to your pore size, pore structure, that's very important to explain such certain things like this, okay? So let's come to the meat again. So well spacing again. So how do I combine all this to well spacing? Remember, this is what we've been used to doing. This black line is dotted line is what people said my stimulated SRV. We tried, we did all the spacing tests. I don't think no company can claim successes in saying that we got the well spacing right. I mean, it's still a work of art, work in progress. I mean, so right now, what I am saying is, let's look at this. After 5 minutes, you had this, and when everything leaked off, there is no more fluid going into the matrix. You have reached a situation with this red line, what it says. It's gone much beyond these fractures, okay? Maybe it's time to look at that volume, okay? So how do you look at that volume? Just the pressure, just the process I described. I injected a known volume of fluid. That's my completion design. I injected that. What I did is I increased the net stress by that much. If you just plot this and get it back to 0, I just increased the net stress of my reservoir. So that's the delta P I observed. So I injected something to a tank. I increased the pressure of the tank by a certain volume. Okay. All this now I have to do is, what's the size of my tank? And that comes to be a simple compressibility equation. You have all seen this compressibility equation. And now if I know the volume of the tank, unfortunately, I have to assume geometry. Okay. What's the geometry best describes? And you have seen so many pictures of SRVs. I think an ellipsoid do fine. Okay, so your one side is your stage length. So people are doing 15-foot clusters these days, 15 to 17-foot clusters. I am pretty sure or positive that I can completely drain 7.5 feet on each side, at least when everything stops, your completely curve takes place. Okay, and then once I know that, all I have to assume is I have only one parameter left, is the hydraulic fracture. This is where geomechanics guys come in, your completion guys. Almost all the companies I know have some kind of a gopher model or a stimulation model. From you have done any kind of hydraulic stimulation models. You actually know what height to expect. Or if you have a good geomechanics guy or a petrophysicist, rock physicist, something, they will just read that off your sonic law. sometimes. Okay, so you can do that and then get an estimate. So, and the good thing is we're not going to plug one numbers. We got to do this in stochastic. Okay, and this is how we get to the part. We know the net stress. We know what we pumped in. Now we can compute the volume, convert the volume to a geometry. Okay, now here's the things that I don't know. I'm going to deal with. Even after everything has gone into the fracture, from the fracture into the matrix, there is still some volume of fluid stuck inside the pore space created by the propellant. So propellant has a porosity, okay, because it's round in shape, it has a porosity inside sitting there. How do we estimate this? You could get a range by knowing what your propellant density is and your propellant packing. You can assume a propellant packing and get it. Okay, so this is uncertain. Okay. Again, as I said, your height growth modeling from your hydraulic design, there's always, I mean, you give this to two people and they will come up with two different answers. So you take those uncertainties, okay? Change in water saturation. So this is the toughest part. So you have injected this fluid into the matrix, but you made some changes to saturation. If you're good in, doing material balance, you can get this number, but it's the toughest part to mention. But for grains and wiggles, you can assume you've changed 10%, 15%. No, you can change the numbers. So we're going to play with this, okay? And then here's your friendly petrophysicist guys come and say, yeah, here's my saturation in porosity. Remember, he's giving you off your vertical pilot. Things get changed in the horizontal. And that's why I said, do your other studies of cuttings and see if there's changes in the horizontal. Obviously, I mean, you're not going to trust your petrophysics on water saturation. So you're going to assume also an uncertainty on that, okay, on porosity. As I showed you the slope, right? If the data gets scattered, the way you group things, the stages, you have some uncertainty over that, okay? And compressibility is like, you need that compressibility equation. Some people sample the fluids in day 1, some people sample it at day 30. So you have the uncertainties to deal with in compressibilities. And pressure prediction, DFIT, is that the right answer? Or do you trust DFIT? Or you have some other way, what's the uncertainty there? So you capture all of that. Once you capture all that, and you can go into a Monte Carlo simulation and do that. Okay, but remember, the function is the same. The equation I showed you is very simple, right? Compressibility equation, and these are the inputs to the compressibility equation that I have to handle uncertainties. Okay, so finally, your log looks like this. So you can't do this manually, sit there and draw lines of each point. So there's some machine learning we can do, and then here's it. You establish transfer function after filtering for geology, similar lithology. In this one, it's easy. This one is slightly tough, but that's why you get into data science and machine learning. Okay. So what's the end of, so among all this, what am I trying to tell you here is, you went from this plot, okay, a simple delta ISIP versus ISIP plot, all the way to what's your SRV look like? Okay. No money spent, nothing. So the other sponsor I would like to mention is the Seismos guys. So Seismos guys is the one that I envision using there to find out if this is true. Can they predict what's each point and how does it reflect here? So Seismos has a technology that they can do the complexity versus long. So that is where I want to involve people who actually see this kind of measurements and see what you come up with, because now you've just converted the simple plot into this one, and you can see the different changes of the stages. I mean, this one goes 1,000 foot most of the times here. Okay. And you can also play with the variances. For this well, for example, was a tough one. And you could see these stages. These are stages 34 to 50, where you actually went large distances. Okay. It could be two things. One, the pressure is wrong. My assumption of pore pressure being the same is wrong, or this is, but anyways, this is completely different. Your bottom half of the well is at a different, it's fracking differently. So you can address all the variances, and here's your 650, 660 spacing. So now you know what to space your next well at. Okay. Remember, spacing is not just an SRE problem. Spacing is economics and the time of a production. So you got to wait. If this well has been in production for 10 years versus 2 years, yeah, I mean, looking at this, I would put another well at 800. But if it's been 10 years, yeah, I will go probably 1,000 feet. So those are the things you should take care of. So end of the day, so what do you tell the completions manager? You go back and say, look, guys, I've studied multi-wells like this, A, B, and C, or multi-lithologies, and I found out that here's the volumes I pumped in, and here is what I'm affecting. Okay. And if this is our target, a 4 wells bench target, and please do not pump a job at the target, go down to the design, maybe 80% of the design, and say, okay, that is enough to handle, because remember, the pressure is going to dissipate much beyond what I pumped in. So it's going to go. So here's how you save the money. Okay. Save this fluid volume design, come down on fluid volume design, and tell the clients. You might have seen this plot in some of the papers by Devin. I think they have the sealed wellbore modeling, and it's very similar. Now we can get all that by just having a completion data, just delta ISIP and ISIP. Okay. So what are the caveats? I have to explain the caveats. So this is an interesting well. We drilled a well. Here's the gamma ray, and here's the gas shows. Everything was fine. Okay. Until we started seeing high gas shows. Okay. And to me as a person, okay, I already knew what was happening in this well. So, okay, yeah, it's going to be fractures. Awesome. I'm going to find that using my delta SIP, this plot, you know. So I go there and plot this, and lo and behold, I didn't see anything. And now you have some scatter that tells us our targeting was not the best targeting or steering, but why didn't the red stuff come out? You know, that was my first question. I've been telling people that this is a high permeability. I mean, I have to explain this gas. Why is this gas? Lithology is not different. It's the gamma is not that different, but it was different. So then we said maybe I have to invent some other diagnostic plots to go in conjunction with that. So I'm going to introduce you to two conjunction plots. Before that, so I looked at the MSE again. Okay, always plot the MSE against gamma and see where it actually starts to deviate. Okay, and you see the MSE is very high here. Okay, and you have the gas shows. So I knew what was happening. So this is again, I said I use the MSE for fracture magnification. So I like, okay, if you remember this, when you have lots of fractures and you're drilling through these fractures and plates, it's going to be much harder to drill. And that's what it's been showing here. You're spending more time, energy to drill the well. So finally we said, okay, let's do another, you know, I come up with two more diagnostic plots to treat this. So these are kind of useful if you guys are working on unconventionals. It's going to be called the relative change of ISIP. That is your delta ISIP divided by the original ISIP, and your stage number. So you can now see where it actually starts deviating. Okay, now I can explain this. Okay, there's something happened here. I don't know what, but it looks like stress shadowing happened all the way here, and then it went. Okay, stress shadowing will happen if you have a high permeability. You know that all those things. And again, this curve is always do this. You know, you take your average treating pressure and plot them against the average MSE for the stage, and you will see that as well. So both of them is this a diagnostic tool you should be using to find out what happened to the well in terms of fractures. Okay, so you can see that here. Okay, I can clearly see what happened here. I can also clearly see, if I don't have the MSE, I can also see what happened here. Okay, that's my recommendation. So final caveat is the time. What happens between 5 minutes, 10 minutes, 15 minutes? Okay. So we had some wells. So I did the experiment. We brought in many wells, like 2 or 3 wells. We measured 5, 10, and 15, and they started plotting. So this is an example for 5 minutes. Here's 10 minutes. It's close, but it's not that close. I mean, it's not actually the same. So there is some things that's going on. So, but you do not have the luxury of going more than 15 minutes. People will ask you to stop. So maybe 15 minutes is where I will go. And also, I am assuming this transfer function to be linear. In future, is it really linear? That's the question. But imagine this as your Horner plot. You know, you have a build-up and you draw a linear line to go to your P star. So that is the kind of methodology. And in future, I want any professors or students looking at this, I would like to see if there can be an analytical solution. Okay, when you do RTA, most people come up with this fancy term called square root of K over X and times XF. If you think of this is your root of XF. You know, the way this line is moving up and down depends on permeability. The slope of this thing is a function of surface area. So in future, maybe I haven't had a chance to look into this, but maybe somebody can, and then maybe I'll give him partial credit for this. So, but that's the idea. Okay, so probably that's all I have, and I don't want to bore you with the conclusions and stuff. So I've gone through a lot of stuff. So it's pretty much your detection of faults and fractures, your identification of your well performance, your lithology to effective lithology, and your well spacing. So I will take questions now. And I'm going to also thank the sponsors for sponsoring my talk. Okay.
Thank you, Dikman. Thank you for all that. As stated earlier in the presentation, please submit your questions through the chat window. I'm going to go ahead and get started. We have had questions already through the talk, so please submit those through there. First question, how do you use the method plot, or Alfred plot, to deal with stages that may have interfered with one another? One stage may already be pressuring up the next stage, interfering with it. It may yield an anomalous delta P with your pore pressure and interpreted shift observed if there is no interference.
Okay, so the way to answer that question is I'll go here. So if your stage is already pressured up, right, your ISIP is already going to increase. Like, you're going to have spend more time to break it. So most people look at ISIP as one single variable. I have done the same mistake as well. People just go and plot ISIP and see the changes. So it is not about the ISIP, never about the ISIP. It's about the change in ISIP as a function of ISIP. So if you didn't have this y-axis here, all these red lines will plot like this, like always increasing, right? You're increasing this line. Okay, so you're going from, if you don't have this y-axis, your ISIP is going to increase like this as a function of stage. So you are seeing that. You are seeing the effect of interference. But the question is, they're all similar stages, so they are going to form a line. Okay, it's all about SRB. I'm creating similar stages. Increase in that pressure is not important. I mean, it is important. If they don't come in the same lines, then it has a different geometry. If it is a different geometry, they don't belong to the same group. Does that answer the question?
I'll let him get back.
Okay, I can't even ask that. So yes, the pressure is being felt, but it's all about the delta change, not about the absolute value of ISIP. That's what I'm trying to say.
Sure, and if you want to follow up those questions with the discussion, I know Dikman, you said you were available for
yeah,
questions
I mean,
afterwards.
you can notice my address, or you can find me on LinkedIn. I can always answer the questions. Okay.
Right. Next question. We don't know the density of hydraulic frac swarms. How do you account for this in your well spacing comments?
Here. I don't, well, the whole idea is I have no idea before I drill the well and frac about any fractures. Okay, I have no clue. Okay, I mean, you can use your curvature map to say something, but you have to, I mean, there are a lot of people question the value of curvature, but if you have some curvature, that's fine. And there's one validation. So let's assume that this is the well I just fracking, and suddenly there is a stage that goes here. Okay. My problem is not to go and define the density of fractures here. All I'm saying is that stage 250 feet stage length or 200 feet stage length, I had a very high leak off. Okay, fine. Okay, maybe that's the stage here. Okay, that's my stage. All right, can I move this? Okay, that's the stage that created leak off. Now, all I can do at this point is come back and say, do you find anything in the seismic in this direction? Or if you just plot your MSC logs, or you drill 5 wells, do you see anything in any direction that actually can track this? You use that information and not avoid this, avoid fracking or putting big design into that stage. That is all I can do. And I cannot get density of fractures. If the density of fractures are here, I'm equating this to a higher permeability of leak off.
Okay. Next question, how would you interpret leak off from pre-existing cracks from an older parent well geometry when you don't know much about the parent completion, cluster spacing, stage length, etc.? Would that be some of the noise in your data set?
No. So what I am going to say about that is I don't say I won't care. This is about very completion independent. Like, all I know is this is after the fact. You've used whatever design you want. This is after the fact. Okay. This well here is your parent well, for example. I don't know what happened, what design it caused to the parent well, but all I'm interested in these points. Okay. So so my question is, I think what he's trying to ask is, your parent might have created some effects to the present ones. Is that the question? Okay. So it'll all get reflected here. Okay. If you have, let's say you have leaked off and you're at a lower pressure, you have drilled the well in a lower pressure, this point automatically moves here. This, whatever if the blue was, the well B was at a lower pressure, this well B would be shifted here. Okay. They would automatically go here. So you would find out that the reason why it's actually going lower is you have actually drained the reservoir, because lower pressures will always move to the left. And you will get easy, I mean, your energy to frac that stage will be less. So you're always going to go to the left.
All right.
Again, it's a very independent to any kind of completion. It doesn't depend on what completion design. All it matters is these points where they fall. And I've had a chance to look at the Eagleford as well as some Bone Spring wells. It all works. I mean, it's still holding well. So
Awesome. Well, with that, everyone, I want to thank Dikman Alfred for taking the time to and agreeing to give this talk. It really does mean a lot that people give back to the community through these technical discussions. I think we can all learn from each other's experiences, especially in this time. And I also want to thank, importantly, the sponsors for today's event. So Diversified Well Logging and Seismos, thank you for sponsoring this event. We really appreciate it. Without you, these kind of events wouldn't be possible. And we look forward to working with you guys in future events that are applicable. The talks are applicable to your technology.
thank you guys. It was a pleasure.
Absolutely. Thank you, Dikman. Well, with that, guys, I want to respect everybody's time. This has been the HGS General Lunch. Please go into the event page, check out sponsors, look on the calendar for future events. I'd love to see you attend, or connect to us on social media to find out about things that might interest you. All right. Everyone, take care. Thank you so much, and be safe out there.